Hello dear students, let me begin the next lecture. In this lecture we will solve two examples of calculating the line integral of a given vector field. These two examples are quite simple. In the first example we will calculate the line integral of the vector field f over a curve C, where the vector field f is given by x square y I unit vector plus x square plus y j unit vector, and the curve C is the parabola y equal to x square from origin to the point 2, 4. And in the second example, we have to calculate the line integral of the vector field f equal to x square I unit vector plus j unit vector around the circle x square plus y square equal to 4 traced once in anti-clockwise direction. So let me start the solution. We will solve the first example by two methods. In the first method, we will use the definition of the line integral of the vector field f over the curve C, and according to this definition, this line integral is equal to the definite integral from a to b of f dot r prime of t. Okay, and in the second method we will use the second definition that we have learned in the theory lecture, and according to that definition, if f has components p, q and r, then this line integral becomes equal to the line integral over the curve C p dx plus q dy plus r dz, and then we will take any one of the variable x, y or z as parameter. In this example I will take x as the parameter. Okay, so let me start the solution by first method. We will take x as the parameter, so it means that x in terms of t is equal to t, and from the equation of the curve y is equal to x square, so y in terms of t becomes y equal to t square, since x in terms of t is just equal to t. Okay, and since x varies from 0 to 2, because we have taken the piece of this parabola starting from the origin and ending at the point 2, 4. At the origin the value of x is 0, and at this point 2, 4 x is equal to 2. So it means that in this curve x varies from 0 to 2, and since x is equal to t, so it means that t also varies from 0 to 2. Okay, so therefore the parametric representation becomes r of t equal to x of t, which is equal to t I unit vector plus y of t, and y of t is t square j unit vector, and the variation of t is from 0 to 2. So this is the complete parametric representation of the given parabola starting from the origin and ending at the point 2, 4. Hopefully this is now clear to you, and this was the main task in this method. Since in the first method we want to use this definition of the line integral of the vector field, so it means that we have to express f in terms of t, and we also need r prime of t, that is the derivative of r with respect to t. So we will find both of these terms. First we will express f in terms of t. For this we have to replace x with its value in terms of t. Since x in terms of t is equal to t, so therefore in place of x square we have just t square. Similarly, since y in terms of t is t square, so therefore in place of y we will write t square, so that f equal to x square I unit x square times y I unit vector plus x square plus y j unit vector becomes t square times t square I unit vector plus t square j unit vector. Very simple. This simplifies to t raised to the power 4 I unit vector plus 2 times t square j unit vector. Hopefully this was very simple to you. Now we will move forward. We will use the definition, and since a here is 0 and b is 2, because t varies from 0 to 2, so therefore a is 0 and b is 2. Now we will put the value of r to calculate its derivative with respect to t, since r is equal to t I unit vector plus t square j unit vector, and we will also put f in terms of t in the next step, so that we have this in the next step. the derivative of t with respect to t is just 1, so therefore t I unit vector is just equal to I unit vector, and the derivative of t square with respect to t is 2t, so therefore t square times j unit vector is simply equal to 2t j unit vector. Now we will calculate this dot product. For this we will multiply these two vectors component wise, and then we will add the results so that we have this thing. Now we will integrate this by using the power rule of integration, so that the result is this one, and then we will apply the limits of integration. We don't need to apply the lower limit of integration because it is 0, and on the lower limit of integration t raised to the power 5 and t raised to the power 4, they both become 0, so we will just apply the upper limit of integration so that the result is 112 divided with 5. Okay, this is the answer. Now we will obtain the same answer using the second method, in which we will use the components. So this is the second definition as I illustrated initially. Now we will put the values. Since the given vector field is f equal to x square y I unit vector plus x square plus y j unit vector, so it means that p is equal to x square times y and q is equal to x square plus y. Okay, so put these values here, and similarly we have next 0 times k unit vector, so r is 0. Okay, so therefore we have 0 here. The final term goes 0, so we don't need to write it in the next step, so that we have this. Now we will take x as parameter, and since the given equation of the curve is y equal to x square, so it means that dy is equal to the derivative of x square, that is 2x times dx. Okay, so in place of dy we will have 2x dx, and since we have chosen x as the parameter, so it means that we need the variation of x. Since, as I have already illustrated, that x varies from 0 to 2 because we have the portion of the parabola which starts from the origin and ends at the point 2, 4. So it means that x varies from 0 up to 2. So therefore dy is equal to 2x dx, and x varies from 0 to 2. Hopefully this was clear to you. Now the right hand side becomes x square remains as it is, and in place of y we have just x square, and then x square again remains as it is, and dx also remains as it is, and in place of y we have just x square, and dy is equal to 2x times dx. So hopefully this was very clear to you. Now this simplifies to x power 4 dx plus 2x square times 2x dx, and this further simplifies to by taking dx as common from the right. We have x power 4 plus 2x square times 2x, which is 4 times x cube. Okay, now again apply the power rule of integration with respect to x, and then apply the limits of integration. We get the same result, 112 divided with 5. So this is how we can solve the line integral of a given vector field by using the second method. Now we will solve the next example. In the second example, we have to calculate the line integral of the vector field f equal to x square I unit vector plus j unit vector around the circle x square plus y square equal to 4 traced once in anti-clockwise sense. So here the curve is a circle x square plus y square equal to 4. Its radius is the square root of 4, that is equal to 2. So this is a circle of radius 2, and its center is the origin of xy plane, as it is clear from the equation of this circle, and it is traced in the anti-clockwise direction. So if this is x-axis and this is y-axis, and if this is the point 2, so the circle starts its journey from here and it moves in the anti-clockwise direction, and it is traced just once, so it completes its journey at the point where it started its journey. Okay, and it is traced in this direction, anti-clockwise direction. So it means that the parameter t varies from 0 to 2 pi. Very simple. and in the solution we will use the first method, so therefore we have to use the parametric representation of the circle. And we know that the parametric representation of a circle of radius a, if it is traced completely, is radius times cos t I unit vector plus radius times sin t j unit vector, and t varies from 0 to 2 pi. Okay, so the parametric representation of the given circle is r of t equal to 2 times, here 2 is the radius, cos t I unit vector plus 2 times sin t j unit vector, and t varies from 0 to 2 pi. Okay, now we will use this definition, t varies from 0 to 2 pi. Now we will put f in terms of t and the derivative of r with respect to t. It is clear from the parametric representation that x is equal to 2 times cos t and y equal to 2 times sin t. So f in terms of t becomes x square I unit vector, which is 2 cos t whole square I unit vector plus 1 times j unit vector. So this is just 4 times cos square t I unit vector. Okay, and we also need dr by dt, which is equal to 2 times minus sin t I unit vector, that is minus 2 sin t I unit vector plus 2 times cos t j unit vector. Okay, very simple. So put these values down here and take the dot product. By taking the dot product we get this result, very simple. And now we will apply the linearity principle of integration, that is we will separate out the integral over the sum so that we have this result, very simple. And now we will write the first integral in this way. It has been taken outside the integral as it is constant, and minus is used with sin t. Okay, because the derivative of cos t is equal to minus sin t, and we want to use the power rule of integration on this term cos square t. Okay, so that the result of applying the power rule of integration is this, very simple. And the integral of 2 times cos t is simply 2 times sin t. Apply the limits of integration, we have this result, and this becomes equal to 0. Very simple. Cos 2 pi is 1, so we have this result, which is 1 cube, and 1 cube is 1. And cos 0 is again 1, so therefore we have this result, which is 1. So 1 minus 1 is 0, 8 times 0 is 0, so the first term vanishes. And sine 2 pi and sine 0 are both 0, so therefore the second term also vanishes, and the result is a 0. So this is the answer of this example. Hopefully you have understood this. This completes our today's discussion. Thanks for watching.